Hi everybody, welcome to another video in Calculus 3. We continue review with calculus vectors in 3 dimensions or 3-dimensional space. Right. So in 3-dimensional space we have x, y, z coordinate, or simply we use r to the third power, or we just say r3 is the set of all the point x, y, and z. And in that case, we'll get to that in a minute. But first of all, how do we set up the x, y, and z? So you see there's a right hand here, kind of. Okay, probably you see better. There's a right hand there. So the right hand, the way it goes is that we have the x-axis and then the y-axis. And then the z. So the way it goes is this. This is the right hand rule. So we use the right hand. It looks kind of backward on the camera, so I just use this. So you put the index finger in the direction of the first vector, and then you curl the fingers. Put the fingers in the first vector, and then curve in the second, and then the thumb will be the z coordinate. Right, so that is the right hand rule. So potentially, if I just unname it, just go like this. If I have 3 coordinates like this, how do we say it? Right, so we'll start with x, y, and then that will be z. Why does that work? Put the fingers on the first the x, and then curve that in the y direction, whatever the thumb goes, if we indicate. Now if I do pretty much the same thing, if we have 2 coordinates, and if I switch, I have x and y here, to put the fingers on the x and then curve in the y direction, it will point down. So the z in that case is that. So I have to obey the right hand rule like that. So in that case, put fingers in x and then curve in the y direction. The thumb will indicate the z direction. Right. And set up on all the pairs, on all the triplet x, y, z. So the setup on this x, y, z is called the R3 rectangle coordinates. Right. So the way we do this is it's kind of difficult to draw 3-dimensional space in 2-dimensional object, meaning the paper here. So in that case, we have to kind of create an illusion. And if we have x, y, and z, say x, y, and z, if we just say the point here, kind of difficult to see. However, if we say it goes like this, then at least we know what that point is, where that point is. I mean, let's do that. Right. So it's like that. So if we want to write A, B, and C, we go A in the x direction, B in the y direction, and then Z in that direction. Right, I see how it works. Let's plot the point 3, 4, and 5. First, let's divide the axis into increments, so at least we know what that is about. So 1, right. So x, we have 1, 2, and 3. So we start from 3 on the x. Next we go to y is equal to 4. So the y-axis I divide to 4. So nice thing about this is we don't have the scale doesn't have to be the same. I mean, this much will be 1 in this x-axis, but different on the y. So we have, first of all, let's label this. We have x-axis, the y-axis, and then there's the z. So First we'll go in the x-axis and then go to parallel to the y axis, and we'll go this much. So first we go 3 the same with the x-axis, and then go in the direction parallel to y, and then z is equal to 5. So again, let's see, 2, 3, 5 will be right there. So we're going to go 1, 2, 3, 4, and 5. That point is 3, 4, and 5. So we go 3 in the x-axis, 4 parallel to the y-axis, and then 5 up parallel to the z-axis. So that point is 3, 4, and 5. So that's what we draw in 3 dimensions. So if we just draw a dot, it's impossible to know what actually it is. Right. Same thing here. -2, -3, and 5. So we go. First of all, this is the positive x-axis, y, and those are z. It is z. Alright, -2, so 1, 2. We go back, and that is -2. And then y is -3. So this is positive. So we have 1, 2, and -3. Okay. So it will be parallel to that. And about that much. In the y-axis. And then z is 5. Well, for that parallel to the z-axis, so it will be way up there. Not very good, but at least that's how we do it. So -2, and then on the y, and then z. So it will be very difficult to see what time the actual those lines to guide to the point. Right. So that should be simple. Yeah, of course it will be like 1, 2, 3, 4, 5. Right. Now equation of simple plane. This is the simple plane for xy. We're going to have z equal to 0. Xz plane is y equal to 0. YZ plane x equal to 0. Pretty much whatever missing here. We also have x equal to constant, y equal to constant, and z equal to constant. Like x equal to 2 will be parallel to y, x equal to 0. Y equal to 4 is parallel to y equal to 0. That is y equal to 0. And then z equal to 3 parallel to z equal to 0. But it go to where z equal to 3 instead. Right. Distance, midpoint, and equation of a sphere. Right. Distance. Way back in cosine algebra, we have distance, midpoint, and equation of a circle. Now we extend that into 3 dimensions. Distance formula. So if we have 2 points, distance between P and Q is going to be given by that. Of course, we extend Pythagorean theorem in 3 dimensions. That's simple. The midpoint of the line segment drawn in the points P and Q is given by this. Pretty much, if we want to simplify, we can say just the point P plus the point Q divided by 2. So the average of the x-coordinate, y-coordinate, and z-coordinate of P and Q. That's pretty much it. Equation of a sphere. So this is a sphere. If we don't have the z component, that is the equation of a circle. Now we have one more equation of a sphere. The center is at ABC, radius r. So that's what we have. The equation of a bone. The bone is inside of the sphere and the sphere itself. So kind of a solid 3-dimensional object. and the center is still at ABC, and radius r. The only difference between the bone and sphere is normally it is equal to, which is a sphere. We have less than or equal to. That's why make it a ball, including the interior of it. So if we have anything less than, will be inside. If we want to describe anything outside the sphere, it's going to be greater than the radius square. Right. We have a simple example here. Consider the point P and Q. Find the equation of the sphere with the line segment PQ as a diameter. So if we have PQ as the diameter, meaning that the center is going to be in the midpoint of the diameter, right? First of all, the midpoint of P and Q. So let O be the midpoint of P and Q. So the coordinate of O is equal to P plus Q divided by 2. So we have the point 1, -2, and 5. The book don't write this notation, but at high level that is perfectly acceptable. Like I said, later on a point is a vector is a point. So we can just add them like a point is even though it might be a vector, but those are the same thing. Anyway, so what we actually write is not in this form, but in the other form. Should have 1 and 3 divided by 2, -2 and 4 divided by 2, 5 and -5 divided by 2. So first the average of x components, y components, and the z component. And so we have 4, so it will be 2. 2 will be 1, and that will be 0. Right. And next, I should write smaller. Right. So we have the midpoint, which will be center. Right. Then we need to determine the radius. The radius is going to be half of the diameter, right? So radius r is equal to half of the diameter. We could draw an arrow on the top, is perfectly fine. Anyway, so we just take the square root. I said I should write a lot smaller. Anyway, so x minus x, x2 minus x1, or x1 minus x2 doesn't really matter. Let's say 3 minus 1 then. And then 4 minus -2. Sorry about that. And then 5 minus -5 square. Right, we do that, and we have 3 minus 1, so 2 square. -4 minus -2 will be 6 square, and then 10 square. Right. We don't really need the square root. We just do the square inside the square root only. That's 140. So square root of 140. Right. Of course, it's not right. Don't forget, we talk about the radius, so that's 1/2. If we bring the 1/2 inside of 140, either I have to have more space or I have to write smaller. 1/2 bring it inside, become 1/4, and we have square root of 35. So this is the radius and this is the center. So the equation, I have to write that here. So it's going to be x minus 2 square plus y minus 1 square plus z minus 0, so we just have z square equal to square root of 35 square, which is 35. So the equation of the sphere is given by that. Sorry about the spacing. I should write extremely small. Right? Right. So that's good. Next, we have this equation. Right. So not in exactly the right form for either sphere or a ball, but we know it's going to be, could be a ball or could be something else. We need to turn this into the right form first. So I will group all the x together, bring the 2x next to it, y square, bring the y next to it, then z square next to the z. Now we do complete square. We're going to add something to make this a complete square. So we add something here. Plus y square plus 6y. Add something. SZ square minus AZ. And then add something there to make a complete square. So remember, we add 3 things on. Once again, I write too big. 1, 2, 3. So we add 3 times on the left, we add 3 things on the right to keep things balanced. So the way we do a complete square, you should know this already. We'll take half of this, and then we squared. So half of that is minus 1. Minus 1 square is 1. If you add 1 here, add 1 there. And then take half of this, which is 3. And then we squared, will be 9. So you add 9 here, add 9 there. And then half of negative 8 is negative 4. And then we squared, will be 16. If you have 16 here, we have 16 there. Okay. Now the left hand side will be a bunch of perfect square. So the way we do this, half of the middle term square. By the way, we only do this when the coefficient of the square is 1. If this is something else, we have to divide by that number. So if it is 1, we can do this just fine. Then we just say x minus 1 square, y plus 3 square, and z minus 4 square. See, just add the x, the y, and the z and make a square. And then on the left hand side, negative 1, 1 cancel, 9, 16, 25. So we have this less than or equal to 25. So this is the ball. Center. The center will be at 1. This will be y minus negative 3. And then 4. And radius, square root of that. Right. So that is the equation of a ball. Once again, sorry about that. Right. Next, vector in R3. So now we have more precise. Earlier we only talked about 2-dimensional space, a ball, point, and other things. Now we go to vectors. Let P and Q are vectors. Then the point PQ is given by Q minus P. So there's nothing new. This is exactly the same as 2-dimensional case. and we have 3 dimension, still the same. And then u, let's say be a scalar, a number. U and v are vectors like that, and u plus v, we add the components, subtract the components, and multiply all the components by that constant. So there's nothing new here. Now find the components of the following vector 2 times u. So pretty much we take 2 times the vector u. Before -8 and then 2. That's easy enough. Remember, we can also use the calculator. If you use that, if you use a calculator, we use second parentheses, use the bracket, like the set of numbers, 2, -4, and 1, close the curly bracket, and we do that for -2. So, simple enough, straightforward. And then u plus 2v, 2, -4, and 1, that is u plus 2v, 3, 0, and -1. So we just multiply first. Multiply 2 and 6, 0, and -2. And then we combine them. 2 and 6 is 8, -4 and 0, and 1 and -2 is -1. Right, I said it just sometimes the easy, simple calculation gets me. Plus 2, 3, 0. If we have to use negative, it is this negative and not the subtract sign. Close the curly bracket. Right. And then u minus 3v, 2, -4 and 1. That is u, and then minus 3v, 3, 0, and -1. So let's multiply only the 2 inside. -9, that's 0, minus 3 times -1 is 3. Now we subtract 2 minus -9, that's plus 9, 2 plus 9, 11. Minus 4 minus, still minus 4, 1 minus 3 minus 2. Right, since you already entered that in the calculator, we just go back here and change the plus 2 to minus 3. And we have that. Sorry, we multiply and that should be plus 9. Okay, we multiply by 3, not multiply by -3. So if we still keep the minus here, so it will be 9, 0, and -3. Right, so be that. So in that case, it's not this. So be careful. Just multiply the numbers 9, 0, and -3. Now we just have the subtract. So 2 minus, so that will going to be 2 minus 9 minus 7, minus 4, that's correct, and 1 minus -3, that is 4. Right. Oh, yeah. So just be careful. I usually just multiply the number first, and then we subtract. Right. So we just have vectors and operation on vectors. Simple enough. Now, the magnitude of a vector, a unit vector, are 3. Now we did this in 2-dimensional case. Now just add one more component to it, and we have 3-dimensional space. So we still have PQ equal to that, and because we just say that PQ is just the final minus initial, the head minus the tail. Right. And then the distance from P to Q is the same as the magnitude PQ. So the distance between P and Q is the same as the magnitude or the length of the line segment PQ. So the formula here and the formula we have before is exactly the same. Right. Now we will have the same thing here except in 3 dimensions. So we have I 1 0 0, so we just have the x component. So that is I. And then we have j 0 1 0 is only the j component. And then the k only the z component. Then the vector will be given in this form. Right, well, we talked about that. We just have v1 times this, so we just have the v1 in the first component, v2 only affect in the second component, and v3 affect in the third component, and then we combine them. We have those two are equal. Right. Now consider the points 5, 3, and 1, negative 7, 8, and 1. Express vector PQ in terms of unit vector ijk. Right. So first we just find the vector PQ. Vector PQ is final minus initial. Final minus initial. So we write that in terms of the notation for a point. But when we put in the vector, it's going to be negative 7, negative 5. That will be negative 12. 8 minus 3, 5, and 1 minus 1, 0. So vector PQ is given in that form in the bracket notation. Or we can write negative 12 for the first component, that is I, then 5, second component, and then there's no k, or we can just say 0 vector k, or just say negative 12i plus 5j. Next we find the magnitudes of vector PQ. So this is easy. Vector PQ, the magnitude will be given by that. What do we have before? Now, so according to the vector, we just take the square root of the component. So I just say we have the magnitudes of the vector negative 12, 5, and 0. By the way, from previous section, I did mention that sometimes we see the double bar, sometimes we just see a single bar. It's still fine. As long as we understand that we're talking about the magnitude, the distance on the length. So just have square root of the square of the component. So this is Pythagorean theorem. So that gives us 13. Means square root of 169, which is 13. So magnitude is 13. Next, I'll find the position vector magnitude of 10 in the direction of PQ. Before we do that, we have something I forgot to write this. We have the unit vector in direction of V. So this is a little note we need to know here. So unit vector, which is the length, a vector of length 1, unit vector in the direction of V. another vector. We did do this in the first section. So the unit vector in the same direction as v is given by vector v divided by the magnitude of v. Usually we denote this a unit vector, the vector whose length is 1. Right, so first we're going to write out u, vector u, the unit vector in direction of PQ. So let's start with that. U vector PQ divided by the magnitude of PQ. PQ is negative 12, 5, 0 over 13, which is the magnitude we calculated earlier. And then we divide each of them by 13. So we have negative 12 over 13, 5 over 13, and then 0 over 13, still 0. Right, so we know that this vector has the length equal to 1 and in the same direction of PQ. So when we divide vector v by a scalar or multiply by 1 over a scalar, so pretty much when we multiply a number to a vector, we do not change the direction, right? So when we have the vector multiplied by a scalar, does not change the direction, or divide by a scalar does not change the direction. And then now we want this to be the magnitude is equal to 10. So pretty much what we do is we multiply 10 to vector u. So have 10, negative 12 and 13, 5 and 13, and then 0. So we have negative 120 over 13, 50 over 13, and then 0. So it's simple enough. Right. So we just do the same thing but 3 dimension. When I do this video, after the first video, I realized I can just go a little bit quicker on the first few sections. It's just a review in calculus. When we actually get to the calculus part, even though if we have to use some of this again, we still have a chance to practice this concept. Right. We have an application problem here. So a plane is flying horizontal due north in calm air, which means there's no air. When it encounters the crosswind is that, and the downward draft blowing vertically downward at 30 miles per hour. Right. So usually if we have just 2 dimensions, then we know that for sure. For 2 dimensions, north is up and S is on the right. Now how do we put this in 3 dimensions? So in 3 dimensions is north X or Y. Alright. Now it will be easier to think about this way. If we just navigation just have everything in 2-dimensional space, if we consider that north is in the y-axis and A in the direction of x-axis, now we will put that into the z. It will be like this. So if we say this is x, y, and z, alright, the right hand rule, the x is corresponding to the east direction and y is corresponding to north, and then up is up. Right. So with that, we have a plane flying due north. So we said there's a vector of the plane just say this vector p for the plane due north 200 miles per hour, so only north direction, right? So vector for the plane vector p north 300 miles per hour. So if we're going to write the vector p, it's only one with the north. I mean, in that case, north is y, right? And we have all of them in 300 in the y. So on x and 0 for z. That's y for the plane. Now for the wind, it encounter cross wind. Cross wind will be on the same plane as the airplane going, so it's only x and y. So it's going to be southeast at 40 miles per hour. So again, crosswind, so it's only on two-dimensional space, and so we can refer back to this two-dimensional northeast. We talk about southeast. So if it's southeast, then that will be exactly 45 degrees. Now we can decompose this into the x and the first and the second component, or x and y component of this. So in that case, if we're talking about the wind, in direction of the first component is adjacent to it, so we're going to have cosine, and the magnitude is 40, so the length of this is 40, so we're going to take 40 cosine of 45 degrees. Let's just get an estimate approximation here. Is that in degree mode? Yes, it is. Right. 40 cosine 45, right, about 28.28. That's also miles per hour. Right, W2. By the way, this one to the right, so it's positive. W2, or this, is opposite to the angle. Opposite, so it's going to be sine 45 degrees. Sine 45 is the same as cosine, so it's going to be 28.28. The difference here is this one, because it's pointing down, so it will be negative. And then the third component, there's none. So we just say the wind, we have the vector as the first component is 28.28. The second component negative 28.28, and there's nothing going up or down, so it'll be 0. And then we have the downward draft, so it's going to be down, magnitude 30 miles per hour. So this is easy. That vector is equal to 0, 0, and 30 on the third component. And I will just add all of this up. And when we take the magnitude, we have the direction. Right. I'll take the magnitude, and we have the speed. Let's ignore the direction here, because it's kind of difficult to determine that. Not until the next few sections. Right. So we just add all of them up. So velocity with respect to ground with respect to the ground. So it's going to be velocity of the plane plus of the wind and the downward draft. Now add all of this up. So add all of them up, and to 0, that's 28.8 on the first component, 300 minus that, to 71.72. That's just 2 decimal places, and then 0, 0, and 30. So that is the velocity. If we want to speed, we just take the magnitude. And so magnitude of that, so square root of the square of the components. 28.28 square, 271.72 square, and then 30 square. So square root of, now we can just take this number square plus that number square plus 30 square. Right. So we actually take the whole numbers instead of rounding like we do here. And we have 274.826. So again, 2 decimal places will be good enough. And the unit, all of this, is still mile per hour. Right. So just the basic review in the pre-calculus about vectors, 2 dimension, 3 dimension. So it's not much. Later on, when we go to the calculus, then we use a lot of this basic idea about vectors. But I said when we get there, we have plenty of chance to review. So that's why we didn't spend much time on the first few sections at all. The only thing that I just want to go over this is about the notation. Right? The math should be simple. You should see this before, but just want to go over the notation that we use in class. Namely, we use the boldface for the vector. We don't use the letter with the hat on the top. We use the hat if there's 2 letters. That's for the vectors. But if it's just 1 letter, that's a lowercase boldface. Or we can use the bracket notation. I prefer to use this bracket notation over ij and k, because ij and k we write like this. It takes more space and take more time to write. Use the triangular bracket would be better. But like I said, when we go to the next few chapters, we will do a lot of vectors in this case. So just this first few sections, just get familiar with the notation and stuff. Right, but that's it for this section. Thanks for watching.